என்கேஜ்ல இருக்கா? ஒரு நிமிஷம் இருங்க.
சார்
ஒரு நிமிஷம்.
ஹலோ
ஹலோ.
சார் இந்த யூடியூபுக்கு இங்கே நம்ம டிஸ்பிளே காப்பி பண்ணியிருந்தேன்.
எங்க இருக்குங்க சார்? டிஸ்பிளேலையா?
ஆமாம்.
காப்பி ஸ்ட்ரீமிங் லிங்க் இல்லையா?
வெப்சைட் டாப்ல
பண்ணிட்டேன் சார்.
காப்பி ஸ்ட்ரீமிங் பண்ணிட்டீங்களா?
பண்ணிட்டேன். இப்போ அது லைவ் ஸ்ட்ரீம் ஆயிட்டு இருக்கா?
ஆமாம்.
ஓகே, லைவ் ஸ்ட்ரீம் ஆன் ஆயிருக்கு அப்படிதானே?
ஆமாம்.
ஓகேங்க சார். ஓகே, காப்பி பண்ணிட்டேன் சார். தேங்க்யூ. சார் 1476
சார்.
சார் ரீகன் சார்.
சொல்லுங்க சார்.
ஒரு சின்ன ஹெல்ப் பண்ணுங்க. அந்த டிஸ்கிரிப்ஷன் பாக்ஸ்ல
ஓகே
டிஸ்கிரிப்ஷன் பாக்ஸ்ல வந்துட்டு Fourier's intense influence on mathematical application FDP இருக்குங்க சார்.
ஓகே
சார் அந்த இடத்திட்ட மட்டும் அந்த டாபிக் மட்டும் மாத்தணும்.
அப்படியா? இது யூடியூப் லைவ்யா?
யூடியூப் லைவ்ல அது நேத்து டாபிக் இருக்கு அதுல.
டாபிக் மாத்தணும், ஃபர்ஸ்டே தான் மாத்தணும்.
சரி, ஓகே, அப்படியே இருக்கட்டும், ஒன்றும் பிரச்சனை இல்லை.
இதனை கட் பண்ணிட்டு போடவா?
கட் பண்ணிட்டு கூட போடுங்க, ஒன்றும் பிரச்சனை இல்லை.
டாபிக் மட்டும் எனக்கு சேட்ல அனுப்புங்க, நான் கட் பண்ணிட்டு போடுறேன்.
சரிங்க சார். ஓகே. அப்புறம் டிஸ்கிரிப்டிவ் பாக்ஸ்ல அட்டெண்டன்ஸ் லிங்க் போடணும்.
அது கூட என்ன போட்டு விடலாம்.
என்னங்க சார்? அதுவும் இப்ப நான் கொடுக்கவா? இன்னைக்கு சேட் பாக்ஸ் எனேபிள் ஆயிருக்கோ?
ஆமா.
அப்ப நாங்க சேட் பாக்ஸ்லயே நாங்க அது போட்டுக்கிறோம். சேட் பாக்ஸ் ஃபுல்லா இருக்குல்ல நமக்கு?
கண்டிப்பா இருக்கும்.
அப்ப ஆனா இப்ப யூடியூப் லிங்க் மாத்த வேண்டியது வருமா? மாத்த வேண்டாம், நீங்க மாத்த வேண்டாம். ஏன்னா எல்லாத்துக்கும் ஷேர் பண்ணிட்டோம் நாங்க. இப்படியே இருக்கட்டும், இதை கட் பண்ண வேண்டாம்.
டாபிக் மட்டும் மாத்த முடியுதான்னு பாருங்க.
டாபிக் மட்டும் மாத்த முடியுமான்னு பாருங்க. இந்த யூடியூப் லிங்க் எல்லாத்துக்குமே ஷேர் பண்ணிட்டு உள்ள வர ஆரம்பிச்சிட்டாங்க, அதனால கட் பண்ண வேண்டாம்.
சார் ரெக்கார்ட் வந்து கவுடுக போடுங்க.
ஹோல்ட் பண்ணுவா?
ஆமா. நேத்து ரெக்கார்டிங் போட்டீங்களா?
நேத்து ரெக்கார்டிங் போடல.
நீ போட்டீங்கன்னா கவுடுக போட்டதுன்னு சொன்னேன்.
சார் இந்த லைவ் ஸ்ட்ரீம் ஸ்டாப் பண்ணிட்டு திரும்ப கண்டினியூ பண்ண முடியுமா?
அப்படி பண்ண முடியாது.
பண்ண முடியாது. ஓகே.
ஆமா, எனக்கு லிங்க் சேஞ்ச் ஆகும் ஸ்டாப் பண்ணிட்டு பண்ணோம்னா.
சரி, ஓகே. டைட்டில் மட்டும் எடிட் பண்ண முடியுமான்னு பாருங்க.
நான் பார்த்துக்கேன் சார்.
பிரபாகரன் சார், கேக்குதுங்களா நான் பேசுறது? பிரபாகரன் சார், பிரபாகரன் சார்.
சார் அவர் ஹோஸ்ட் பண்ண சொன்னார் சார். அவர்
இன்னும் கோ-ஹோஸ்ட் ஆலையா?
ஸ்டவ்ல.
ஹலோ
ஹலோ சார். பிரபரன் சார். சார் உங்க ஸ்கிரீன் வியூ ஆயிடுச்சு, நல்லா தெரியுது. ஆடியோ மட்டும் செக் பண்ணுங்க சார்.
சார் கேக்குதுங்களா?
கேக்குதுங்க சார். இன்னும் கொஞ்சம் திரும்ப பேசுங்க சார்.
ஹலோ
கேக்குதுங்க சார், கேக்குதுங்க சார். யூ ஆர் ஆடிபிள் சார்.
இருங்க, எனக்கு நான் பேசுறது கேக்குதுங்களா?
கேக்குது சார், நீங்க பேசுறது கேக்குது.
பட் மத்தவங்க பேசுறது கேட்கலையே.
ஹலோ. இல்ல அவங்கள்ட்ட நீங்க சொல்லுங்க. இப்ப அந்த சாரோட ஸ்கிரீன் செக் பண்ணிட்டு இருக்கோம், அதனால
இப்ப கேக்குதுங்களா? சரி இப்ப
கேக்குதுங்க சார். கேக்குது கேக்குது
கேக்குது. சரி சரி. உங்களுக்கு வீடியோ வருதுன்னு தெரியுதுங்களா?
தெரியுதுங்க சார். வீடியோ தெரியலங்க சார். அது பரவாயில்ல, நம்ம அது ரொம்ப எஃபர்ட் எடுக்க வேண்டாம். நம்ம ஸ்கிரீன் நல்லா தெரியுது, நம்ம இப்படியே போயிடலாம்.
அப்படிங்களா?
ஆமா சார்.
சரி இருங்க.
வீடியோ எனேபிள் பண்ணிருக்கீங்க.
இப்ப வீடியோ தெரியுதுங்களா?
இல்லங்க சார், தெரியல.
எனக்கு இந்த இதுல தெரியுது. ஆனா என்னோட சிஸ்டத்துல வந்து சைடுல உங்களோட வீடியோ தெரியுது, என்னோட வீடியோ தெரியுது.
சரிங்க சார். சார் ஒன்றும் ப்ராப்ளம் இல்லைங்க சார், நம்ம இப்படியே ப்ரொசீட் பண்ணிடலாம். நம்ம ரொம்ப
இப்படியே பண்ணிக்கலாங்களா?
இப்படியே பண்ணிக்கலாம். நீங்க நம்ம யூஷுவல் ப்ரொசீஜர்ல நம்ம ஸ்டார்ட் பண்ணுவோம் சார். கரெக்டா நம்ம ஷார்ப்பா ஸ்டார்ட் பண்ணிடலாம். நீங்க ஃபர்ஸ்ட் ஸ்கிரீன் ஓபன் பண்ணி வச்சுக்கோங்க, நம்ம அப்படியே ப்ரொசீட் பண்ணிக்கலாம்.
சரிங்க சார்.
உங்களோட இன்ட்ரோடக்டரி ஸ்கிரீன்ல ப்ரொசீட்.
சரி நம்ம இப்படியே போய்க்கலாங்க சார்.
சரிங்க சார். ஓகேங்க சார். இன்னும் ஒரு 10 மினிட்ஸ் இருக்குங்க சார்.
பரவாயில்ல, அப்படியே வெயிட் பண்ணலாங்க.
சரிங்க சார். ஓகே.
இப்ப வீடியோ தெரியுதுங்களாங்க சார்?
இல்லைங்க சார்.
இப்ப தெரியலீங்களா?
இப்ப தெரியுதுங்க சார். இப்ப தெரியுது.
இப்ப தெரியுதுங்களா?
இப்ப தெரியுதுங்க சார். அவங்க ஃபேஸ் மட்டும் கொஞ்சம் லேப் மட்டும் அட்ஜஸ்ட் பண்ணிக்கோங்க. இப்போ நீட்டா இருக்குங்க சார். இன்னும் கொஞ்சம் ஓகேங்க சார். இப்போ சூப்பரா இருக்கு.
இப்ப நல்லா தெரியுதுங்களா?
இப்போ நல்லா தெரியுதுங்க சார். தென் இப்படியே செட் பண்ணிக்கலாம் சார்.
அப்ப இது ப்ரொசீஜர். இது இது ஆன் பண்றது, ஆஃப் பண்றது. சரி. ஓகே. ஃபர்ஸ்ட் நீங்க இன்ட்ரோடக்ஷன் கொடுத்து அப்படியே ஸ்டார்ட் பண்ணிக்க வேண்டியது.
ஆமாங்க சார். ஆமாங்க சார்.
ஓகே.
ஸ்டூடெண்ட்ஸ் வந்து ஜூம்ல பார்ட்டிசிபென்ட் ஜூம்ல வர மாட்டாங்க சார். ஸோ நான் தான் கொஸ்டின் செஷன்ல நான் தான் இன்டராக்ட் பண்ணுவேன். சரிங்களா? அவங்க கொஸ்டின் கன்சல்டேட் பண்ணி நான் இன்டராக்ட்.
ஓகே. Most versatile of the transforms is the Laplace transform.
Good afternoon to all. We welcome you all to the FDP on recent trends in applicable mathematics, organized by the Department of Mathematics, Cornell Institute of Technology and Sciences. We would like to appreciate your active participation in the first day of FDP and your kind cooperation. Thank you. Now, we begin this session with the word of prayer by Dr. Rebecca Jabasili Etna.
Good afternoon to all. Let's pray. Heavenly Father, we submit the second day program in your mighty hands. Take complete control of the entire session. Be with us and fill us with your heavenly wisdom to understand the recent trends in applicable mathematics. Be with the resource person and bless his presentation. Let it be useful to everyone. In the name of Almighty God, I pray. Amen. Now over to Xavier, sir.
Thank you, ma'am. Now, I request Dr. Vinainston Vivek J. to introduce today's resource person.
Good afternoon to all. It is indeed a great pleasure to introduce our Chief Resource Person, Dr. Prabhakaran, currently working as Assistant Professor in the Department of Mathematics, Coimbatore Institute of Technology, Coimbatore. He completed his post-graduation and MPhil in Mathematics and also B.Ed in Mathematics Education from Bharatiyar University, Coimbatore. He also completed his doctoral degree in the field of control theory from Bharathidasan University, Tiruchirappalli. His areas of interest are optimal control theory and ethnomathematics. So he has authored a textbook on engineering mathematics and also published several research papers in reputed journals, national and international, to his credit. So he has completed one UGC research project and has streamlined several workshops, faculty development program, and seminars. He is also a member of several academic and scientific bodies. We are happy to have such a young and dynamic person, Dr. Prabhakaran, in our faculty development program as resource person. So we welcome you, sir. Dr. Prabhakaran, sir.
Thank you, sir. Thank you very much, sir. Thanks for your invitation. Good afternoon to one and all present here. I am Prabhakaran, Assistant Professor of Mathematics, Coimbatore Institute of Technology. First, I would like to thank Department of Mathematics, Institute of Technology and Sciences for giving this opportunity. In this forum, let us discuss about Laplace transform and its applications. There are numerous integral transforms that have been developed over the years, many of which are highly specialized. The most versatile of the transforms is the Laplace transform. Many dynamical systems may be modeled or approximated by linear ordinary differential equations with constant coefficients. An indispensable tool for analyzing such systems is so-called Laplace transform. The utility of Laplace transforms is broad. They can be used to analyze signals. They are also very useful for analyzing systems described by ordinary differential equations with constant coefficients. First, I would like to introduce the concept of integral transform. In my lecture, outcomes of the lecture is learning the concept of Laplace transform, relation between Laplace transform and Fourier transform, properties and existence of Laplace transform, applications of Laplace transform with example. In mathematics, an integral transform maps a function from its original space into another function space via integration. Where some of the properties of the original function might be more easily characterized and manipulated than in the original space. The transformed function can be generally be mapped back to the original function space using inverse transform. The concept of Laplace transform is the general form of the integral transform is given by the JBS sir.
சார் சொல்லுங்க சார்.
இந்த பிபிடில இந்த செகண்ட் அப்படி வர மாட்டேங்குது.
Enter கொடுங்க
ஈக்குவேஷன்ஸ் எல்லாம்
என்டர் கொடுங்க சார்.
என்டர் கொடுத்தாலே வர மாட்டேன். அடுத்த பேஜ் போயிருது. இப்ப உங்களோட இருந்து வேணா ஷேர் பண்றீங்களா?
சார் மெயில் அட்டாச் வருதுங்க சார்.
வருதுங்க. ஈக்குவேஷன்ஸ் எதுவும் வரல, டைப் பண்ணது தான் வருது. நான் உங்களுக்கு அனுப்பிச்சிட்டுங்களா?
சரிங்க சார். ஓகேங்க சார், அனுப்பி விட்டுருங்க. நீங்க சொல்றது சொல்லிட்டே இருங்க, நாங்க இடையில இது பண்ணிடுறோம்.
சரிங்க சார்.
இப்ப இதே மாதிரியே வச்சு பிரசன்ட் பண்ணுங்க சார், ஒன்னும் பிரச்சனை இல்லை.
சரி, ஓகே 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 ஓகே.
சார் கண்டினியூ பண்ணலாம்.
Continue. The general form of the integral transform is given by g of alpha equal to integral a to b f of t k of alpha comma t dt. In this equation, g of alpha is the output of the signal and which is a function of alpha. F of t is an input of the signal and a function of t. And the kernel k of alpha comma t is an integral kernel which is also a function of alpha and t. This is the general form of integral equation. But the Laplace transform is given by L of f of t equal to integral minus infinity plus infinity f of t e power minus st dt. Generally, Laplace transform of the function f of t is given by the operation of multiplying f of t by e power minus st and integrating the product with respect to t between minus infinity to plus infinity is called the Laplace transform. This is also integral transformation. Next, we will see the relation between Laplace transform and Fourier transform. The signal x of t, all the signals x of t is represented as the sum of the exponentials of the form e power st. E power st always represents the signals. In the Laplace transform definition, f of s is the output of the signal, f of t is the input of the signal, e power minus st is the integral kernel. Here L is the linear operator. Where S is a complex frequency which is given by sigma plus j omega. Sigma plus j omega. Next, we consider the Laplace transform of the function f of t, that is f of s equal to integral minus infinity plus infinity f of t e power minus st dt. Here put s equal to sigma plus j omega. We will get f of s equal to integral minus infinity plus infinity f of t e power minus of sigma plus j omega of t dt. Put sigma equal to 0. The above function can be rewritten as f of s equal to integral minus infinity plus infinity f of t e power minus j omega t dt, which is a Fourier transform. Therefore, we observe that the Laplace transform is a general case of Fourier transform. Sorry for inconvenience. Laplace transform is the mother of Fourier transform. Mother is Laplace transform. The child is Fourier transform. Mother is Laplace transform. The child is Fourier transform. Therefore, Laplace transform is the mother of Fourier transform. Otherwise, Laplace transform equal to Fourier transform if sigma equal to 0. The sigma equal to 0 means purely imaginary. That is s equal to j plus omega. Here sigma equal to 0. When sigma equal to 0, the Laplace transform coincides with the Fourier transform. The drawback of Fourier transform is Fourier transform do not exist for non-absolute integrable signals, but Laplace transform do exist for non-absolute integrable signals. Laplace transform do exist neither energy nor power signals also. Comparing to Fourier transform, Laplace transform can be applied to broader range of signals. The reason is we are replacing j omega by s. That is sigma equal to 0, purely imaginary. In the complex variable s equal to sigma plus j omega, sigma is known as damping factor. Omega is known as angular frequency. There are two important variants. The number one is bilateral, that is two-sided Laplace transform. In this case, the Laplace transform for all the values of t is given by L of f of t equal to integral minus infinity plus infinity f of t e power minus st dt. The second one is unilateral Laplace transform, that is one-sided Laplace transform, that is positive values for t, that is t greater than 0. In this case, L of f of t equal to integral 0 to infinity f of t e power minus st dt. In our universe, time is king. In our universe, time is king. We describe our reality with mathematical functions of time, f of t equal to some function of t, g of t, h of t, all the functions of t. Our reality always functions of time. Laplace is another universe. Our universe is time, Laplace is another universe. The other universe is frequency, which is given by s equal to sigma plus j omega. The Laplace transforms our time ruled universe. Laplace transform our time ruled universe. Our universe time domain. The Laplace universe is S domain. In time domain, two hands, one for hours, other for minutes. Time domain, two hands, one for hours, other for minutes. In S domain also two hands, one for sigma and other for omega. These are the similarities between time domain to frequency domain, that is S domain. Laplace transform maps a function of t to a function of S, that is time domain to frequency domain. Both domain has two variants. Laplace domain transforms to time domain to frequency domain. Frequency domain is also referred as Laplace domain. Next, we see the existence of Laplace transform. The Laplace transform of f of t exists for s greater than alpha. If point number 1, f of t is piecewise continuous on every finite interval in the range t greater than 0. The second one is f of t is of exponential order. This is for existence of Laplace transform. The first condition is piecewise continuous for all the positive range. The second condition is of exponential order with respect to alpha. The above conditions are sufficient but not necessary. The existent conditions for sufficient conditions, not necessary conditions. Next, we will see the next keyword, piecewise continuity. A function f of t is said to be piecewise continuous in an interval if the point number 1 The interval can be divided into a finite number of intervals in each of which f of t is continuous. The second one is the limits of f of t as t approaches the endpoints of each subinterval are finite. The interval can be divided into finite number of subintervals, and the limits of f of t approaches the endpoints of each subintervals are finite. Both the conditions are satisfies the piecewise continuity. For example, we will see the function at tan t. This is the graph of tan t. Laplace transform of tan t is not exist. For the case of f of t equal to tan t, the function is not integrable over the interval 0 to t. For any t greater than pi by 2, and the function becomes infinity at the pi by 2, 3 pi by 2, and 5 pi by 2, etc. And also it has many discontinuities. Therefore, Laplace transform of tan t is not exist. But next we consider the function x square between 0 to 5. F of x takes x square between 0 to 5. F of x takes 7, 5 to 8. F of x takes 9 minus x, 8 to 9. See this function. The function f of x consists of 3 continuous pieces separated by 2 discontinuities at x equal to 5 and x equal to 8. Hence, the function f of x is piecewise continuous in the interval 0 to 9. The next keyword is exponential order. A function f of t is of exponential order alpha, then limit t tends to infinity, modulus of f of t into e power minus at is finite. This is the condition for exponential order with respect to the order alpha. For example, consider the function f of t equal to t square. Our condition limit t tends to infinity, modulus of f of t into e power minus alpha t. Replace this f of t by t square. Put t equal to infinity, we will get 0. This is a finite. Therefore, f of t equal to t square is of exponential order. This is the example for exponential order. Some exceptional cases is the Laplace transform of root t equal to square root of pi by s for t greater than 0 exists. But the function square root of t is not piecewise continuous on finite interval. Piecewise continuity and exponential order, both the conditions are necessary conditions. But Laplace transform of root t exists, but the function is not piecewise continuous. This is the good example in the exceptional cases. The above conditions are sufficient but not necessary conditions. The difference between necessary and sufficient, I will explain in the beautiful way. Necessary means minimum requirement. Necessary means minimum requirement. Necessary means minimum requirement, that is limited means. Limited means is necessary. Sufficient means more than enough. Sufficient means more than enough. That is full meals. Sufficient means full meals. Next concept is inverse Laplace transform. L of f of t equal to f of s. F of t equal to L inverse of f of s. L is a linear operator. L inverse is also linear operator. The meaning of inverse Laplace transform is the process of recovering the unknown function f of t from the Laplace transform, that is L of f of t is known function. The process of recovering the unknown function f of t from the Laplace transform. This is the concept of inverse Laplace transform. Recovering the unknown function from the Laplace transform. Next, Laplace transform of some common functions. The constant function L of k equal to k by s. Laplace transform of constant is at a constant by s. Next, exponential function. That is Laplace transform L of e power minus at equal to 1 by s plus a. L of e power at equal to 1 by s minus a. The trigonometric functions L of sin at equal to a by s square plus a square. L of cos at equal to s by s square plus a square. In the hyperbolic functions L of sin h at equal to a by s square minus a square. L of cos h at equal to s by s square minus a square. Next, properties of Laplace transform. First property and basic property, linearity. If x of t and y of t are two signals with the Laplace transform capital X of s and capital Y of s, then L of a into x of t plus or minus b into y of t equal to a into Laplace transform of x of t, that is x of s plus or minus b into Laplace transform of y of t, y into y capital Y of s. So what is the meaning of linearity? Physical meaning of linearity, I will explain by suitable example. This is an example for linear system also. Suppose if we apply a brake in a bike, suppose if we apply a brake in a bike, what will happen? Automatically the bike will stop. Meaning of situation, application of the brake stops the bike. This means that we know the output for the given input. This is a linear system. Application of brake may even cause the fall of the rider or some other accident. This happening cannot be predicted. This is a non-linear system. Generally, Laplace transform is useful to convert non-linear system into linear system. Laplace transform is useful and powerful tool to convert non-linear system to linear system. Next, change of scale property. If L of f of t equal to f of s, then L of f of a t equal to 1 by a into f of s by a. When the argument t of f is multiplied by a, then s is replaced by s by a in transform capital F of s and is multiplied by 1 by a. If L of f of t equal to f of s, then L of e power minus at, that is shifting property. If L of f of t equal to f of s, then L into f, L of e power minus at f of t equal to f of s plus a, and L of e power at f of t equal to f of s minus a. The Laplace transform of f of t multiplied by e power at is applied by replacing s by s minus a in f of s, which is the Laplace transform of f of t. Next, Laplace transform of derivatives. Laplace transform of f of t is given by f of s, then L of d by dt f of t equal to s into f of s minus f of 0. Generally, Laplace transform technique is used to solve the system of differential equations and integral equations. Next, advantage of Laplace transform, it gives a particular solution directly. This means that there is no need to first find the general solution and then evaluate the arbitrary constants as in the classical approach. No need to find the particular solution directly. It will give. Next, applications of Laplace transform in science and engineering fields. The first application, analysis of electrical circuits. The Laplace transform is widely used by electronic engineers to solve quickly differential equations occurring in the analysis of electronic circuits. System modeling, second application. Laplace transform is used to simplify calculations in system modeling, where the large number of differential equations are used. The third application is digital signal processing. One cannot imagine solve digital signal processing problems without employing Laplace transforms. Laplace transform is an important tool in digital signal processing. The fourth application in nuclear physics, in order to get the true form of radioactive decay, a Laplace transform is used. It makes easier to study analytic part of nuclear physics. The fifth application is process control. The Laplace transform is used for process controls. It helps to analyze the variables which, when altered, produced desired manipulations in the result. Laplace transform is applied not only in science and technology field, but also in economics. First, we obtain the relation between the present value and the Laplace transform. Consider case of investment project. For various alternatives, one wishes to calculate the present value of series of cash receipts and transactions. Cash receipts and transactions. The present value of a series of payments is given by PV with respect to T equal to sigma T equal to 1 to T C of T divided by 1 plus R whole power T. The left hand side PV is present discounted value at time T. The right hand side ratio, the numerator C of T represented by cash flow. R is rate of discount and T is period. The relation PV with respect to T is given by sigma T equal to 1 to T C of T divided by 1 plus R whole power T. By using an exponential series, that is replace 1 by 1 plus R whole power T by e power minus RT. Exponential series formula e power minus RT equal to 1 by 1 plus R whole power T. We rewrite the above equation, we get sigma T equal to 1 to T C of T into e power minus RT. In the continuous time case, replacing the right hand side summation to an integral, that is integral 0 to T C of T into e power minus RT dt. Summation can be replaced by an integral. Again here T is some finite quantity. Here we consider T tends to infinity. Replace T by infinity, that is integral 0 to infinity e power minus RT C of T dt. By using the definition of Laplace transform, the above equation can be rewritten as L of C of T. The unilateral Laplace transform general format integral 0 to infinity f of T e power minus st dt. Here f of T equal to C of T. Therefore, L of C of T equal to PV with respect to our interest. Therefore, Laplace transform of cash flow is the present discounted value at time T. This is the main application of Laplace transform in the economics. Laplace transform of cash flow is the present discounted value at time T. L of C of T equal to PV with respect to R. The next application in economics, the Laplace transform, we derive the relation between Laplace transform and present value for cash flows using present value. Consider the case of constant cash flow, cash payment K made at the end of each year at interest rate R as shown in the following timeline. First 0, 1, 2, 3, the years. First PV, the constant cash flows, K, K, K. Here the cash flows is continuous forever. Therefore, the present value is given by an infinite geometric series. Therefore, PV equal to K by 1 plus R plus K by 1 plus R whole square plus K by 1 plus R whole cube, etc. Dividing both sides by 1 plus R, we get PV by 1 plus R equal to K by 1 plus R whole square plus K by 1 plus R whole cube plus K by 1 plus R whole power 4. Subtracting the above two equations, we get PV into R by 1 plus R equal to K by 1 plus R. On solving, we get the present value PV equal to K by R. That is Laplace transform of K. The Laplace transform of constant cash flow is constant by R. That is present value. Using Laplace transform equation, if the cash flow is constant, say K, then the present discounted value of a stream at interest rate R is given by L of K equal to K by R. Here K is f of t. Therefore, 0 to infinity e power minus RT into K dt. K is independent of the integral, so we can take outside of the integral. That is L of K equal to K by R. Therefore, Laplace transform of constant cash flow is the ratio between the constant and the rate of interest. That is second application in economics. In the observations, we find two applications. Number one, Laplace transform of cash flow is the present discounted value at time t. The second one is Laplace transform of constant cash flow is the ratio between the constant and the rate of interest. For example, we take one problem. An insurance company has just launched a security that will pay rupees 500 indefinitely, starting the first payment next year. How much should this security be worth today if the appropriate return is 10%? Appropriate return 10%. We solve this example by using the timeline. Here K is 500, R is 10%, constant cash flow. 500, first year 500, second year 500, third year 500. Rate of interest is 10%. The present value was 0. Therefore, present value is Laplace transform of K. That is K by R. 500 by 0.1. That is rupees 5,000. The present value is 5,000. Next, we see application in simple electrical circuits. Laplace transform application in simple electric circuits. Consider an electric circuit consisting of a resistance capital R, inductance capital L, a condenser of capacity capital C, and the electromotive power of voltage capital E in a series. A switch is also connected in the circuit. Then by Kirchhoff law, we get L into di by dt plus Ri plus Q by C equal to E. This is the electric circuit representing our problem. Suppose we make the following assumptions in the above circuit. an inductance of 3 Henry, a resistor of 16 ohms, and a capacitor of 0.02 Faraday are connected in a series with the EMF of 300 volts. At time t, the charge on the capacitor and the current in the circuit is 0. These are the given conditions. Find the charge and current at any time t greater than 0. Let Q and I be charge and current respectively, instantaneous time. Then by Kirchhoff law, L into di by dt plus Ri plus Q by C equal to E. The given L equal to 2, given R 16, C 0.02, E 300. Substitute all the given parameters in the modeled equation and replace I by dq by dt. We get a second order differential equation d square q by dt square plus 8 into dq by dt plus 25q equal to 150. Applying Laplace transform on both sides. Use Laplace transforms of derivatives formulas. Second derivative s square into L of q minus s into q of 0 minus q dash of 0. First derivative s into L of q minus q of 0. After substitution, we will get L of q equal to 150 by s into s square plus 8s plus 25. Taking inverse Laplace on both sides. By method of partial fraction, the right hand side part is separated by 6 by s minus 6s plus 48 divided by s square plus 8s plus 25. Taking inverse Laplace on each element, we will get q by using shifting property. Differentiation of q with respect to t is I equal to 50 e power minus 4t sin 3t. This is required expression for charge and current at any time t greater than 0. The conclusion is transform all mathematics knowledge to nature. We will get and find all the applications. That is my request. Any questions? For further clarification, my mail ID rpcatcbe@gmail.com. My mobile number 9789652826.
So thank you, sir.
Thank you, sir.
Sir, there are many feedbacks, questions, comments, and are being posted in YouTube. So here I have shortlisted some of those. There are many positive comments about your presentation, sir. People have given a large number of comments. And shall we proceed with question and answer session, sir?
Okay, sir.
Shall I ask the questions? And even before asking the question, I would like to read one such comment. Very useful and real world applications are learned. Excellent presentation. So said by Joseph Sagairaj, one of the professor. So I go with the question and answer session, sir.
Okay.
The first question goes by Professor Vishwanathan. What is meant by piecewise continuous function?
Every interval can be subdivided into finite number of subintervals. In the each subintervals be continuous.
Okay, sir. Okay, but he is asking what is how do we define piecewise continuous? He is asking that. Is there any conditions?
Continuous, suppose the function f of x is said to be continuous at the point x equal to a, limit extends to infinity, f of x equal to f of a. This is the continuity.
Yes, sir. Yes, sir. So we say that in every piece the continuity exists. Then we say piece
every piece is continuous.
Okay, sir. Okay, sir. Okay, sir. So
in the endpoints.
Yes, sir. The next question is, what are all the difference between Laplace transform and Z transform?
Laplace transform is continuous mode, Z transform is a discrete mode.
Okay, sir. So we say about that input function must be continuous in Laplace, and
input function must be continuous mode. The Laplace transform, we apply Laplace transform and Fourier transform.
Okay, sir.
In the discrete mode,
Z transform we will use. Thank you, sir. Thank you. And many people were asking one such question, sir. I don't say all the names, but everybody asked such common question. How to convert non-linear to linear using Laplace transform?
First, we model the given situation into differential equation. Okay. By using optimization theory, we will transform a non-linear system into linear system in the given situation.
Okay.
This is the procedure for converting non-linear system into linear system.
Okay, sir. I hope everyone would have to see that how the model could be done using even economic problem and electrical circuit problem you have shown. Thank you, sir. Thank you.
Thank you.
Another question, sir. Does Laplace transform only reduce the number of independent variables?
Okay.
That is a question, sir. Whether Laplace transform only reduce the number of independent variables? They're asking.
No, number of independent variables is different from these questions.
Okay. Okay, sir. Okay. Then, sir, there are many teachers ask this question also. How to solve a system of ODE by using Laplace transform? Can you say the steps or concept?
System of ODE?
How to solve system of ODE?
The ordinary differential equation by using Laplace transform?
Yes, sir. Yes, sir. That is we discussed. But how can we solve system of ODE? They're asking.
Oh, system of equations.
Yes.
In this part, we go to in the system of equations to convert it into, suppose f of x, f of t is single variable. In the system, there are many variables. Convert the system into objective type function, applying optimal Laplace transform. Not directly use Laplace transform. Optimal Laplace transform theory is always there. By using the optimal Laplace transform concept, we will solve. Not using directly Laplace transforms.
Okay, sir. I hope our participants got this particular idea of using optimal Laplace transformation to solve. Thank you, sir. Thank you. And sir, I check. Is there any other question? Can we use in biomedical engineering? Laplace transform can be used in biomedical engineering? Is there any suggestion?
It will be useful in the optimal section. Optimal Laplace transform.
Using optimal Laplace transform.
Optimal Laplace transform.
Okay, sir. So there is another question. Can we solve non-linear differential equations by Laplace transform?
Yes, non-linear differential equations also solve by Laplace transform.
Okay, then. Okay, then. Thank you, sir. I check. Is there any other question further? There is a question. Is there any other real-time applications? Can you say like
in non-linear system?
Yes, sir.
The same example. The non-linear system, we don't know the output for the given input. That is the non-linear system. In the situation, we modeled one situation, we solve it.
We solve it.
Yeah.
Okay, sir. But in
We don't
non-linear,
know the output for the given input is always non-linear system.
yes, sir. Yes, sir. Yes, sir. So you have given the example of bike. How do we apply brake in bike?
Example of bike, brake.
Okay, sir. Thank you. Sir, is there any specific difference between Laplace transform and Fourier transform? What is the difference between Laplace transform and Fourier
Laplace transform is the mother of Fourier transform. The particular case of Laplace transform is Fourier transform.
Okay, sir. In the beginning, you said taking sigma value as 0, we get the,
0.
Yes, we get the. Okay, sir. Thank you. And there is another question, sir. Can we use to solve difference equation using Laplace? Normally, we solve difference equation. Yes, sir. Using Z transform, but there is a professor is asking this question. Can we use to solve difference equation using Laplace? Is it possible, sir?
Skorskas theory is there. By using the Skorskas theory in the optimization technique, we solve the difference equations also.
Okay, sir. Okay. Thank you. Thank you, sir. Thanks. So you have already answered for what is the difference between Laplace and Fourier transform here.
Fourier
Again,
transform.
yes, another question. The same question is repeated. There is a question, who is the father of transform theory? Sir, any idea?
Father of?
Transforms theory.
Father of transform theory is Laplace.
Laplace only. Okay, sir. Okay, sir.
Laplace.
In digital signal processing, can we solve symmetric matrix?
Yes, symmetric matrix also solve.
Is it possible to solve symmetric matrix using Laplace transform, sir? That is a doubt there.
Definitely solved. Sylvester theory is there.
Sylvester theory. Okay, sir. Okay, thank you, sir. I hope the participant have to note.
Any other questions?
Sir, I'm checking. There are questions. There are positive feedbacks. People are being posting many questions.
Sorry for my inconvenience operating the PPT.
No problems, sir. It happens. Thank you, sir. I think they have given many questions. Okay, sir. Thank you, sir. Thank you for your presentation. I hope that we got an unlimited meal in your way of saying through your knowledge sharing. Normally, in engineering, we teach Laplace transformation. Every teacher is teaching in every engineering syllabus we have. But still, in economics, you have given an idea that how we could model a problem and we could solve and so on. I hope every participant would have to be benefited because of your knowledge sharing. Now, I request Dr. Jude Immaculate H to deliver the vote of thanks.
Good afternoon. On behalf of Karunya Institute of Technology and Sciences, Department of Mathematics, I express my sincere thanks to Dr. R. Prabhakar, Assistant Professor, Department of Mathematics, CIT. So the explanation for the necessary and the sufficient condition with live example was really amazing. I hope the session clarifies our doubts and provides a deep knowledge on the application of Laplace transform. Thank you, sir, for gracing this occasion and for giving excellent coverage for today's program. Thank you, sir.
Thank you, madam. Thank you, Xavier, sir.
Thank you, sir. Thank you.
Thank you. Thank you.
Thank you, participants. Thank you, Prabhakaran, sir. We once
Thank you.
again thank you for this knowledge sharing. And we thank all the participants for your active participation in this FDP on recent trends in applicable mathematics. And we'll continue with the next session, the third day session, tomorrow in the same platform at 2 o'clock. Thank you, everybody. Stay safe. Bye.